So my name is Alex Nguyen. This is Lab 2, Projectile Motion, Introduction. I recorded a video of an object being thrown like a projectile. In this case, it was me throwing a crumpled up paper ball. I analyzed the video using the trackers in here, together with motions data. I constructed a computation model over here. For the first one, I used only gravity. The second one, I used gravity and air resistance, and I compared the models. So the purpose of this lab is to observe and measure the position of the projectile as it rises and falls. And the key concepts are the position update formula and the velocity update formula. And you have to know the gravitational force near the surface of Earth was roughly minus 9.8 meters per second or squared. For the first computational model, all you had to do was set this equals, make sure you set this equals 0, so there's no drag force. And I used the momentum principle, F net equals to Fg, because you only had the force of gravity pulling it down, and that was mass times 0, comma, force of gravity, comma, 0. And I updated the rules in the loop, as shown here. And that gave us, this data that I plugged into Excel right here. And then to do the same thing with gravity and drag. So there's two forces acting upon it. I had B equal to this value to calculate drag, and then the force of drag was equal to minus B times velocity squared times the unit vector. Yeah, that's pretty much it. And I had to add gravity plus quadratic drag, and I got this data over here. And you see that slightly alter the data. Maybe the line's a little weird because you don't live in a perfect world. And you get this data over here. When comparing the data, you can see that experimental was a lot similar to the model with G and drag than the model with just gravity. Okay, and for the questions, terminal velocity question. So in the y position, y of t, sure, the gravity only peak height is too high. With drag, the peak height and descent curvature match the data better. But in the x of t position, the drag model shows a gradual reduction of horizontal speed consistent with the actual measurements, and that did it better. So terminal velocity occurs when the net force is 0. With drag, that is mg equal to b v squared of t. So for example, with mass equaling to 0.0071 kilograms and b equaling to 1.5 times 10 to the power of -3 kilograms per meters, vt only equal to 6.8 meters per second. So the projectile does not fall long enough to reach that speed. So the graphs approach, but do not reach that flat line. The gravity only model cannot predict the terminal velocity. If I needed vt directly, I would just drop the model from a larger height to let the speed approach a steady value, then fit b using b equals to mg over vt squared. So for the what if the speed's the same speed straight up question, I'd say, so we keep the same initial speed, v naught equals to 3.56 meters per second, but launch it only straight up from the y position, 0.739 meters. So without the drag, the time to ground solves yt equals to the quadratic equation, the quadratic formula of t being the variable, and then plugging the values gives about 0.89 seconds. But then with the angled throw, using the initial velocity with the only y component equal to 3.165 meters per second, the time was about 0.828 seconds. So straight up is longer because the vertical component is larger and the peak height is higher, including the drag. The total time remains longer than in the angled case, since drag reduces ascent and also slows ascent. And that's really it.